Good morning, sir. Good morning, sir. My name is Harika. Today's my topic is Maxwell's two equations for electrostatic fields. Maxwell's two equations for electrostatic fields. Introduction to Maxwell's equations in electrostatic. In this Maxwell's electrostatic, there are two types: Gauss law and the relationship between E and V. Maxwell's equations describe the fundamental behavior of electric and magnetic fields. In electrostatic, the magnetic component is typically zero. Simplifying these equations in differential form, delta dot E equals to rho by epsilon naught. In integral form, integral of E dot dA equals to Q by epsilon naught. These equations are essential for understanding the distribution and the behavior of electric charges at rest. Maxwell's first equation, Gauss laws for electricity. In this Gauss laws of electricity, the statement is given that the divergence of electric field E is equals to the volume charge density divided by the permittivity of free space. Means delta dot E equals to rho of epsilon naught. Delta dot means divergence, delta cross means curl. In this Gauss law, it says that delta dot E equals to rho by epsilon naught. In integral form, epsilon integral of E dot dA equals to Q by epsilon naught. Total electric flux through a closed surface equals to the enclosed charge divided by the epsilon naught. Gauss law's first Gauss law, the derivation of the Gauss law is given this. Gauss law states that the total electric flux phi through only enclosed surface is equals to the total charge enclosed by that surface. Means phi equals to Q enclosed. First, consider a first epsilon. In this differential form, phi equals to integral of d phi. Means total d dot ds. The total charge enclosed is Q equals to integral of rho v dv. Means this is the value. Q equals to integral of s ds. Here this is given as surface. By applying divergence theorem to the middle term in this equation, have integral d dot ds equals to integral of divergence of d dot dv. Consider as a fourth equation. Comparing equation 3, equation 4. Equation 3, equation 4. Integral of rho v dv equals to integral of divergence d dv. By cancellation integral, rho v equals to delta divergence of d. The Maxwell's first equation states that the total volume charge density is the same as divergence of electric flux density. Maxwell's second equation. Again, the first Maxwell's Gauss law is applicable for point. The applications are point charge. Applications of Gauss law is available for point charge and infinite line charge, infinite sheet of charge. Maxwell's second equation. Relationship between E and V. Maxwell's second equation. The potential difference between A and B is independent of path taken. VBA equals to minus VAB. We consider as potential difference between A and B. Here given a one diagram A to B. First consider as a VBA. Again, ఇక్కడ ఇచ్చిన డయాగ్రామ్లో ఫస్ట్ విఏబి అనుకుంటే ద ఆల్టర్నేటింగ్ డయాగ్రామ్ ఈస్ విబిఏ. అంటే ఆపోజిట్లో వెళ్తున్నందుకు we are considered as a minus. We consider as a minus. VBA plus VAB equals to total potential charge E of dl phi of EDL equals to 0. This shows that the line integral of E along a closed path as shown in the figure must be 0. That implies no network is done is moving a charge along a closed path is an electrostatic field. అంటే this implies that no network is done is moving a charge along a closed path in an electrostatic field by applying Stokes theorem. So integral of EDL equals to curl of EDS equals to 0. So curl E equals to 0. The second Maxwell's equation is curl of E equals to 0. Equation 1 and 2 indicates the Maxwell's second equation in this integral form, whereas equation E is in differential form. Maxwell's second equation states that the line integral of the electric field around any closed path is 0. In differential form, it states that the curl of electric field E is 0, showing that electrostatic field is conservative. Maxwell's equations are given in this diagram. Applications of Maxwell's equation in electrostatic. Maxwell's equations are used to determine the electric field in complex geometrics. They help analyze the behavior of capacitors, dielectric materials, and charge distributions. These applications are fundamental in designing electronic and electrical devices. Maxwell's applications are used in point charge and infinite line charge, infinite sheet charge. Maxwell's second equation is used for finding boundaries and the capacitors Finally, the summary. Gauss law provides a foundation for understanding charges distribution. The potential and field are interconnected through the gradient relationships. Boundary conditions and differential equations are crucial for solving electrostatic scenarios. Here, the Maxwell's equations del dot T equals to rho V considered as a Gauss law. Del cross E equals to minus dou B by dou T is the second equation. Thank you, sir.